Okie dokie. I'm going to share my screen with you guys. Let's go to the first thing that I want to talk about, what's due today. So by midnight tonight, you have to have your rock cycle poster handed in. Here's some of the rock cycle posters that people have handed in that I still have to grade. They were handed in last night. But we are going to go into period 1. I was told that I was allowed to share. Not that one. Where are you, Lexi? Okay. So here's Lexi's. And she said that it was okay to share it. And I'm not looking for, this is fantastic. Okay. I mean, there's no other way to say that this is fantastic. It's very comprehensive. What I want to know is that you understand the whole cycle itself. And this, besides it being neat, organized, colorful, and aesthetically pleasant or pleasing to the eye, she's also got all the information in here. And it talks about everything and the arrows that go in all the directions. Remember, the rock cycle doesn't just go in one direction. Rocks can become themselves or any other rock. So we don't just want a rock cycle in which it's just going in one direction. You can see that it's going this way, that it's going that way, that it turns into itself. She's got the information on here. She's got the words, sediment, deposition. She's got deformation. I have to find it. Deformed. Here we go. Rocks become deformed, deformation, weathering, melting, crystallization. Those are all in there. So that's a fantastic poster by Lexi. And then I got this one from Emmy, and she said that I could share it. And I thought, oh my gosh, look at those rocks. They're so cute with the little happy smiley faces and everything, which is great. And then I saw this, there's this poor elephant, this guy's trying to hold up this poor elephant, but because of the pressure going into the metamorphic rock. So she did a really, really cute poster here. Here are all of her examples of the types of rocks, all the different arrows. They are color-coded arrows. She added a key about how they're color-coded. There are sediments of rock, there's deposition, there's weathering, there is deposition, deformation, there's more deformation over here. She's got this whole thing dialed in. Like this is very, very comprehensive as far as having everything in. And I know that looking at this, she understands how the rock cycle works. Okay. So that's the first thing that I wanted to show you guys. I'm going to stop sharing right now because I want to go over if you have any questions. Paige said that I could share hers if I like. Thank you, Paige. I will. Anybody have any questions about what's expected of you for that poster, though? It's due tonight. Now, again, let's talk about expectations. My expectations are what I wrote in the paragraph of what you should have, right? You need to have the 6 words: melting, crystallization, weathering, deposition, sedimentation, and deformation. You have to have those 6 words on your poster. You also need to tell me about sedimentary, igneous, and metamorphic rocks and how they cycle within the rock cycle. And an example of each type of rock. Okay. So I'll get to yours in a second, Paige. Besides that, let's see, we're going to go over what you guys should have in your tile. Do me a favor, everybody, right now, go into your science tile and make sure that module 13 shows up, and let me know if you have module 13, please. Thank you, Ileana. Okay, good. Yeah, if a couple of you have it, then everyone has it, right? Okay, thanks, Luke. Thank you, Ileana. All right, so I'm gonna share my screen with you guys. And here we are in my period 2. And period 2, we have our modules. And we are finishing module 12, right? Your rock cycle poster is due tonight, February 12th. Please make sure you have all that information in it that I told you guys about. And complete anything that's in here. You'll notice Brain Pop, and many people have played Brain Pop. Some people were having hiccups when it came to Brain Pop, so I sent out an email yesterday to all the students and parents to make sure that you were getting into it the correct way. The district did buy it for us to use on Canvas, so you have to go in under your EDU account, and I sent out an email last night about how to do some troubleshooting. Here we are on module 13. Today I'm going to be showing you guys a slideshow, but first I'm going to go through here. So you're going to be taking a couple of notes today after I go through module 13. Now, I usually don't push out modules at the end of the week. I usually push them out at the beginning of the week. But because Monday is a day off, I wanted to make sure that everybody knew what they were expected to do for next week. Usually my assignments are the module name and then the number 1 for Monday, 2 for Tuesday, 3 for Wednesday, 4 for Thursday, 5 for Friday. But because you're off Monday, I don't want you guys to sign on onto Canvas. Take the day off, go enjoy it, do something. I plan on, taking my kids to the snow. So get out and do something if you can. So this is what you're going to do. You don't have me on Tuesday, but I still need you to go in and do this. So module 13.1a is going to be for Tuesday's work. There's some reading in here about continental drift and plates and the plate boundaries. And it talks a little bit about Alfred Wegener. And I have a slideshow to talk more about Alfred Wegener, but it talks about the different types of plates and what happens when those plates come together. Whether they come together, convergent boundaries, pull apart at divergent boundaries, or slide past one another at transform boundaries. It talks a little bit about what happens at each one. After you read that, there are 2 videos about continental drift. And we're going to speak more about that in a couple of minutes. And then there's a little video on here, and it's about a scientist. He's a German scientist. His name is Alfred Wegner. Alfred Wegner was way ahead of his time. And he came up with this theory of continental drift. And he came up with this theory back in 1912. And I'll talk to you more about it when we get into my slideshow. But for this part of it, after you watch the video, after you hear about my slideshow, after you read about continental drift and plate tectonics, you're going to pretend that you are a scientist at the same time as Alfred Wegener. And you're going to take the information as a scientist from 1912 would do. You're going to have the same information as Alfred Wegener, the same knowledge. And you're going to have to tell me, if you were a scientist back in 1912 with Alfred Wegener, would you have supported his theory or denied his theory of continental drift? But besides saying that you support it or you deny it, you have to give me 2 pieces of evidence as to why you would support his theory. And then you're going to respond to one of your other classmates about their stance on it, and if they support it or they don't support it. But you need to give at least 1 piece of evidence from the reading when you write back to, or when you respond to the student. So that's what you're going to be doing on Tuesday. I did see that I had some things in the chat, so let me open that. Why do we have off on Monday? Because it's President's Weekend. And you guys are all up here with me, yeah. It's President's Weekend, and the following Monday is Lincoln's birthday. All right, so that's the first thing that you're going to do. on Tuesday. Then on Wednesday, there's more information about plate tectonics. Now, when you guys were learning about the rock cycle, we said in the beginning that, you know, there's the crust, the mantle, the outer core, and the inner core. And that's something that you've already learned back from elementary. But now we're adding to that they're broken down into layers called the lithosphere, the asthenosphere, and the mesosphere. And so they talk a little bit about the asthenosphere and the lithosphere in here, because the plates are on the lithosphere, but the asthenosphere is what causes those plates to move. So it talks about that and what happens at the different boundaries again. Today's Lincoln's birthday? I don't know. Santi, you have 2 3-day weekends, and it's because of President's Day. Okie dokie. The next page, after you read that, there is a video on seafloor spreading. So seafloor spreading is really important. It is the evidence that Wegener was missing when he proposed the theory of continental drift. So they're going to talk to you about seafloor spreading, which is where the boundary is divergent. It pulls apart and it creates new seafloor. Okay, Washington is nice. Yeah, I got them confused. It's Washington and Lincoln. Okay, so seafloor spreading is something that is like a key ingredient or a key piece of evidence to proving continental drift. So after you do that, there's this chart here, which is really cool. It just tells you what happens at each of the 3 boundaries, and then the plate interaction here with the subduction zone. So those are really good notes to have. They will, especially here, they will help you with your quiz. You want to make sure that you have these notes. Then it comes to a lab. So what I'm going to tell you about this lab, and I had one student do it already. There's a couple of things that you have, a couple of options that you have for a lab. Now, I can't hand out all the supplies for this lab to everybody individually, but what I did is I took 2 video simulations from YouTube. And this one here, you can see that he's got pudding and graham cracker. This one here looks like pudding and graham cracker also. And that's what we use when we're in school doing it. If you have pudding and graham cracker at home, you can use that, or you can use something else that is like that if you want to do this lab, okay? So if you don't have pudding and graham cracker, that's okay. There are other things that you can use. They've given you ideas: Oreo cookies, Play-Doh, paper, fabric, hard-boiled egg, graham crackers, frosting, candy bars, etc. If you tell me that you don't have any of that at home and you still want to do the lab, go back to being 5, 6, 7 years old. Okay, kids love to play in the mud. Make some mud and do it with mud. Okay, there's nothing saying that you have to eat it, obviously. If you use food, you can eat it, but you can still do it with mud, so you can see the simulation if you want to complete the lab yourself. You can also watch the lab here, and then the next page has the lab itself as far as written out. Give it a minute and it's going to upload. Okay. So here are the instructions and the materials and the different plate boundaries and what you have to do for the lab. And here's this section, part 1. There are 5 questions to answer. You need to answer those 5 questions. Part 2, 4 questions to answer. You need to answer those 4 questions. Part 3, 4 questions to answer. You need to answer those questions. There are multiple ways to hand this in. You can either hand it in as a website URL, or you can upload the file. But I also added in here a media recording, because if you do the lab and you want to record yourself doing the lab, that would be fantastic. That would be a lot of fun. Okay. So if you can, and you want to record it, that would be great. I'd love to see what you do. And what materials you have to use to make it happen. Do you have to go to the store and buy materials? No, you can use mud in the backyard, right? Okay, so after that lab, the last thing that you guys have to do is a quiz. It's 45 points. Complete the quiz and you are done with module 13. Does anybody have any questions regarding module 13 or what you need to have done? Anybody? Here we have some things. Yummy mud. Mud pies. I know, right? Okay, good, Aliana. Good question. Okay, I'm going to review a couple of questions, or a couple of words, I should say. Part of your rock poster, you're supposed to have 6 words in there, right? And melting happens when the rock becomes magma. Yeah. Another word is weathering. Weathering is when rock is exposed to weather like rain, sleet, snow, hail, sunshine, whatever it is, and it breaks the rock down into sediments. The next one is deposition. Those sediments are deposited and then they're cemented together to make another sedimentary rock, or the sediments are pushed deeper down into the earth. When they go deeper down into the earth, the rock itself that's made is going to go through deformation, okay, which means that it's going to become deformed. Deformation, same, look at the word, break the word apart, deform. The rock becomes deformed and it becomes metamorphic rock because it's under a lot of heat and pressure. That deformation or that metamorphic rock can then rise up through the volcano, right? Become magma, become liquid. And then here's your question, Aliana. Crystallization. Crystallization happens when a rock is becoming igneous. Now, we know all rocks that come from a volcano are igneous rocks, whether it's from magma, internal, intrusive igneous rock, or whether it's lava, external or extrusive igneous rock. That magma has to cool to create a hard rock, right? Otherwise, it's liquid rock. When it cools, depending on how slow or how quickly it cools, depends on the size of the crystals that are going to be found in the rock. So crystallization is when magma is cooling. Something like obsidian looks like a sheet of black glass, and it's a type of rock. And what happens is when magma is released from the volcano, the obsidian cools really, really, really fast. And it doesn't allow any time for crystals to be formed inside the rock. When magma cools slowly, that's when it allows for crystals or crystallization to happen inside the rock. Does that answer your question? Aliana? Okay, good. Anybody have any other questions about the rock cycle? No. Okay. We're going to take a couple of notes. So take out some paper. The notes are going to help you with module 13, especially with the discussion that you're supposed to have about Alfred Wegener. So I'm going to share my screen with you guys, go through a little story about Alfred Wegener here. Alfred Wegener is a well-known scientist. Like I said, back in 1912, he came up with this theory of continental drift. What he surmised is that the continents, the 7 continents as we know them now, used to be together as one large continent. This one large piece of land or landmass was known as Pangaea. And this existed over 200 million years ago, okay? And now we look at Pangaea and we have 7 continents. Like, well, how did that happen? So Alfred Wegener suggested the theory of continental drift because he noticed different things. He had pieces of evidence, but he couldn't prove them. And because he could not prove it, people, his peers, kind of like poo-pooed him. They're like, you're kind of being really silly. This is not true. You know, they ridiculed him. And a lot of scientists of his time did not support his theory of continental drift. And there were some scientists that did. He came up with this idea back in 1912, and it wasn't until the 1960s that they actually, the hypothesis became a theory because of the theory of plate tectonics, which wasn't proven until the 60s. So unfortunately for Wegener, he was dead at the time. He died in 1930. So he wasn't around when when the science community accepted his theory of continental drift as a whole, you know, the science community as a whole. So here's Pangaea. And if you look at Pangaea, our one large landmass, you'll see over here is Eurasia, which is Europe and Asia. We have North America, South America, Africa, Antarctica, India, and Australia. And there are some questions coming in. That's okay, Santi. This is the one large landmass that Wegener said was, you know, what we started with. And then once that one large landmass started to separate, it was separated into what's called Laurasia and Gondwana, okay, Gondwana land. And then it broke down even further. Now, he had some pieces of evidence, but he couldn't prove it. The pieces of evidence that he had was the jigsaw puzzle, and it's not like one that you put together yourself. I'll go over that. Fossils, which are extremely important in this, and rocks and climate. I'm going to go over each piece of evidence that Wegener came up with, and you want to use this information for your post on module 13.1c. So Wegener came across, and he was looking at the continents, the 7 continents, and he's looking at them and he's like, wow, look at this. The border of South America, the eastern border of South America, really looks like it fits into the western border of Africa, like a jigsaw puzzle. If you go back here, you'll see how the pieces would kind of fit together as a jigsaw puzzle. And so he said, well, this is some evidence I have. They used to fit together. It's kind of crazy to think that this wasn't once one large landmass, because you can put them together. And they were still not buying it, right? And then he said, okay, how about this? Here is this fern that existed 300 million years ago. It's called the Glossoteris fern. And he said, how about this? If I look at all the continents and put them together, right, as that jigsaw puzzle, you will see that on each one of the continents, there are fossils that are the same. And this Glossoteris, this type of fern, the fossils are found in Australia, Antarctica, India, Africa, and South America. 5 different continents. Now, we know Antarctica is a very, very, very cold continent right now, but at some point it was not, because this fern was able to survive in all this land, and they have proof of it. There are fossils. There's also these reptiles, fossils of these reptiles that are found, like this one here is found in Africa, India, and Antarctica. This one was found in South America and Africa, and this one's South America and Africa. Now, they're reptiles. Can you imagine? Let's go back to here we go. The reptile is found in Africa, and it's found in South America, those fossils. That reptile did not swim all the way across the Atlantic Ocean, okay? Some are found, like here's Antarctica down here, and you're looking at some of the Glossoterises up here, and all the way down here. Look at the change in the difference in climate, right? So he's like, we've got proof here. All of these fossils that we found, they prove that, you know, it used to be one large landmass. There's no way that they would have crossed the Atlantic. There's no way that this could have survived in the temperature, right? So I'm not talking about climate change. I'm talking about here, these were once in the same area, and they had therefore relatively the same climate. And then those continents moved further apart and the climate did change, not because of climate change, but the climate changed because of its location to that of the equator, right? So that talks about climate. Lastly, the rocks. And the rocks showed those fossils in them, and there were different types of rocks. I'm sorry, the same type of rock that were found on different continents. So he said with all of this information that we had this once one large landmass, and the scientists are like, okay, well, how did they separate, right? So you say you have this evidence of fossils and climate and fitting like a jigsaw puzzle and stuff like that, but how did they become 7 separate continents? Like, how did they move? And he said, well, that's the one thing that I don't have evidence for. And they were like, well, you know, you're dreaming, buddy. If you don't have evidence for it, we can't support it. It wasn't until 1960s that they came up with the theory of plate tectonics. And what happens with the theory of plate tectonics is that the plates are actually moving. Now, there are 7 continents, but there are tens of plates on the, you know, that make up the lithosphere. So it's not like each continent has its own plate. The North American continent is made up of, I believe, 3 plates, and how those plates interact with one another. And what they learned through the process of seafloor spreading. And that's why I said it's really important to watch that video. What it's saying is that the seafloor is diverging, it's pulling apart. And if the seafloor is diverging or pulling apart, new magma is coming up, right? Because we know that heat rises. So the magma from the asthenosphere is rising up, and then the cooler magma is going to be deposited, and it's going to rise up and be deposited and rise up and be deposited. When that new magma rises up through that divergent boundary, it creates new seafloor. So you think, wow, that's really cool. That means our Earth is getting bigger, 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 bigger. It's not, right? Remember, we can't make any more of what we have. It can change, but matter is matter. It never gets lost or destroyed. We can't make any more. We have what we have. So what they said, the scientists said, is that because of the theory of plate tectonics, those plates are moving, and when you're at a divergent zone, it's creating new seafloor. Where does the old seafloor go? Well, the old seafloor, the oceanic crust, is more dense than continental crust, which means that if continental crust, or when continental crust meets oceanic crust, it'll compete. But because oceanic crust is more dense, it's going to subduct or go underneath the continental crust. So that old oceanic crust goes down deep into the asthenosphere, gets heated up, and then it'll come back up into one of those divergent boundaries, creating new seafloor. So the Earth never gets larger per se. The Earth recycles itself, okay? Because you can't make any more matter than what we already have. So that new rock comes up through that divergent boundary, and the old rock goes back into the Earth. And they're able to tell that that's happening because of the magnetic striping in the oceanic crust. And you'll hear about that in the video. So Wegener, you know, you take what you know about Alfred Wegener, you listen to module 13.1, you read it, take that information and imagine yourself in 1912 working with Alfred Wegener, and do you support him or do you deny him? And that's how you have to answer the question. Does anybody have any questions about Module 13.1c, Alfred Wegener, when he started, what he came up with? Any questions about that? And you're all quiet, so I'm going to assume that's a no. All right, I'm going to stop.